Hi everyone, my name is Sanjay Chouhan and welcome to my YouTube channel. So in this NLP series, we are currently discussing deep learning for NLP. And in deep learning for NLP, we have discussed RNN. So RNN is a basic neural network for NLP tasks. We have discussed the basic structure of RNN and how it works. Now we'll discuss LSTM. LSTM is an improvement over RNN because RNN has some issues. The main issue that RNN has is short-term memory. Basically, if the sequence of the text is very long, then RNN won't be able to remember the beginning of the sentence, the beginning of the text while processing. So it will lose the information from the beginning of the text, and it will only remember the recent tokens information. And to mitigate the issue, LSTM was introduced. And full form of LSTM is long short-term memory. Before discussing more about LSTM, let's look into the basic of RNN. We discussed the RNN in the last video, but I want to reiterate some points from the previous video. So we have seen how the sentence however is processed over time. And this is the basic structure of RNN where we have the input and then the output is looped back into the neural network itself. So the hidden state is again provided as input to the neural network. And we see this example. This is unrolled RNN over the whole sequence. So we are unrolling the RNN over the whole sequence. Basically, this is for different time step. The RNN is only one neural network, and we are processing the tokens from the sequence one at a time through the neural network. But to showcase how the whole sequence is processed, we have shown four neural networks here. But in reality, it's a single neural network. And at different time, we are providing one token from the sequence. So at first, we are providing the first sequence. We get some output. And in the same neural network, we are providing the second sequence along with the output from the first sequence. So it's a single neural network, but we have unrolled over different time steps to show the working of RNN. The first word in RNN is recurrent. That means something is repeating, right? Or reoccurring. So that's what is happening here. We are calling the same neural network repeatedly with different inputs from the sequence. So that's why the name is recurrent neural network. Basically, it's a simple feed-forward neural network only, but it's a reoccurring. That's why it's a recurrent neural network. So let's zoom into an RNN. So this is a internals of a RNN or recurrent neural network. This is a standard RNN where we have single layer. This is a single layer of 10S neural network. So here, not a single node or single neuron. This is a layer of neuron. So that means there will be multiple neurons here. What we are doing here, we are concatenating the input from the current time steps and the hidden step from the previous time step. So HT minus 1 is the hidden step from the previous time step, which is the output from the previous time step, and XT is the input from the current time step. We concatenate both of them and pass through this neural network layer, which is of 10S activation function. So the neurons in this layer are having 10S activation functions, and we get the output HT, which is the hidden state for the current time step. So if you expand this, if you zoom into this 10S neural network layer, I'll see something like this. It's a single layer neural network where we have multiple activation function. All are having 10S activation function. Okay. We're getting inputs and all of them are producing some output. So this is the basic of RNN. So now let's look into LSTM. We saw that the RNN has a single layer, single 10S layer. But in LSTM, we have four interacting layers. So there are four neural network layers in LSTM. So this is a single unit of LSTM where we see there are four neural network layers, and all of them are interacting with each other. So in this single LSTM unit, there are multiple things happening. So we'll discuss this in step-by-step manner so that it's become clearer. Let's first look into the legends. Okay. So here we are using the yellow color box for neural network layer. We are using pink circle for pointwise operation. It can be circle or oval here. Okay, so this is for pointwise operations, and we are using this kind of arrow for vector concatenation, and for representing vector copy, we're using this kind of arrow. So if you look at this, we'll be overwhelmed. So let's look into this one step at a time so that it's much easier to understand. The core idea behind LSTM is cell state. The cell state is the this sign. Okay, we are representing cell state with C, and CT minus one is the cell state from the previous time step, and CT is the cell state from the current time step. In this horizontal line, which is passing at the top, you see there are some minor interactions happening here and here, and these interactions are adding and removing information from the cell state. The cell state is also called like highway of information or conveyor belt of information. Basically, it allows information to be passed from the beginning of the sentence or beginning of the text or beginning of the sequence to the end. The cell state helps in mitigating the issue of short-term memory. And so the LSTM can process very long sequences as well because the cell state allows information to be passed from beginning of the sequence. So if the information is important, then it will be passed. So we'll look into an example. So let's look into this text. This is a paragraph. The guide reminded everyone that Simla would be the final stop. The four of us sat together in our cabin as the train clattered on. Around us, passengers opened tiffin boxes, passing around pakoras and tea, while we treated ourselves to hot parathas from the pantry. Children rushed through the aisles, their laughter echoing above the hum of the wheels. The sun dipped low, and the loudspeaker announced the last station. Last station. A quiet anticipation settled over the train. The last station is mentioned in the beginning of the sentence, or beginning of this paragraph. Simla would be the final stop. So the last station refers to the Simla, and the LSTM will uh, pass this information, Simla, as the last final stop through the network towards the end. Let's first look into the first component of LSTM, that is the forget get layer. I have highlighted the forget get here in this diagram. It is responsible for removing irrelevant information from the cell state based on the current input and the previous hidden state. The forget get has the sigmoid layer, and the sigmoid layer will output values between 0 and 1. And input to the sigmoid layer is the current input, which is xt, and the previous hidden state, which is ht minus 1. So we concatenate both ht minus 1 and xt and provide it as input to this sigmoid layer. And then the output is ft, which is of same size as the cell state. And the sigmoid layer will output values between 0 and 1 for each of the value of cell state. If the value is near to 0 or 0, then that means we need to remove that information, or we need to forget that information. And if the value is 1 or near to 1, that means we need to keep that information. So that's how the forget get layer operates. So let's look into the formula for the forget get layer. You see that output from the forget get layer is ft, the vector, and is equals to sigmoid of wf dot concatenation of ht minus 1 and xt plus BF. So this is concatenation of the previous hidden state and the current input. And we are doing a dot product with the weight matrix of the forget gate, which we are representing with WF. And we are summing up the bias term for the this sigmoid layer BF, and will pass through the sigmoid activation function. So this is how the output FT is calculated in the forget gate layer. So now let's look into the second component, that is the input gate layer and also the candidate steady state. Just like the forget gate layer, when we are removing information from the cell state, the input gate layer is essential for adding information to the cell state. So it puts into the current input and the previous hidden state, and based on that current input and the previous hidden state, it will add information to the cell state. So the first sigmoid layer we see here in this highlighted diagram is the input get layer. So we see that the input to the sigmoid layer is similar to what we have seen as for the forget get layer. It's the concatenation of the previous hidden state, which is ht minus 1, and then the current input xt. So it concatenates both the vectors and passes input to the sigmoid layer, and the output from the sigmoid layer is IT. IT is the output for the input get layer, and you can see the formula here as well. IT equals to sigmoid of WI concatenation of HT minus 1 comma XT plus DI. So we are having this weight matrix WI, which is the weight matrix for the input get layer, and we are multiplying this concatenation of this previous hidden step in the correct input plus the bias term, and we are passing through the sigmoid layer. So let's look into the second layer, that is the trainers layer. Here also we are inputting the same uh, concatenation of previous hidden state and the current input, and we're getting output called C tilde T. So this C tilde T is a candidate cell state. It's a vector of new candidate values that could be added to the cell state. And I'm saying could be because the IT vector will determine which part of the C tilde T can be added to the cell state. The IT vector is coming from the sigma level, and the values in the IT vector will be ranging from 0 to 1. And when we do pointwise vector multiplication between IT and C tilde T, the important information of the C tilde T will be kept, and non-important information of the C tilde T will be removed. So C tilde T is equals to 10x because we are using the 10x activation function in this layer. We are having this WC matrix, which is a different matrix. Which is the weight matrix for this neural network layer. And we are multiplying with concatenation of HT minus 1 and XT, plus this is the bias term from this neural network. So this is how the candidate cell state is calculated. We'll see how this multiplication happen and how the values are updated in the cell state. Let's look into updating the cell state. We're updating the cell state from CT minus 1 to CT. And while updating, we are doing two pointwise operations. One is pointwise multiplication and another one is pointwise addition. And in pointwise multiplication, we are forgetting some information from the cell state. And in pointwise addition, we are updating or adding some information in the cell state. So here you see we have the FT, which was from the forget get layer. So FT is the vector which will be responsible for getting some information from the cell state. And the values in FT vector will be in 0 and 1. And 0 means forget that information, and 1 means keep that information. So when we do a point-based multiplication of vector FT and CT minus 1, so here we are multiplying FT and CT minus 1. Wherever we have 0 in vector FT, in that corresponding position, the value after multiplication will become 0. That means we'll forget that information. And wherever we have 1, we'll keep the value as it is. And in the second operation, before doing pointwise addition, we are doing pointwise multiplication of vector IT and C in the T, or the candidate cell state. The candidate cell state is the new candidate values that can be added to the steady state. And I'm saying that can be, that means it will be added if after multiplication with the vector IT, it remains. Because you see the IT vector is similar to the FP vector. Here also the output is coming from the sigma layer. So the IT vector is also going to be having values between 0 and 1. And wherever we are having 0 in IT vector, the corresponding values in C tilde T after multiplication will become 0. So if it is becoming 0, that means we won't add that value to our steady state. And if the value will remain, then we'll add that information to the steady state. So this input get is making sure that which part of the candidate steady state can be added to the steady state. So this will remove the unnecessary information and keep the required information from the candidate steady state. So after multiplying this IT vector and C tilde T vector, we'll add this to our candidate steady state. So um, this is our formula for the CT. So this is how we update the CT, that is steady state. So CT is equals to FT and the pointwise vector multiplication of CT minus 1 plus IT and pointwise vector multiplication of CT by T. This pointwise vector multiplication is also known as element product. So this is how we update the steady state. So now let's look into the output gate, which is responsible for creating the new hidden state HT. Same as before, this sigma layer also take the concatenated input from a previous hidden state and the current input, that is HT minus 1 and XT, and feed it into this sigma layer, and the output we get is OT. So here also the values will be in between 0 and 1. The OT vector will determine with which part of the steady state to keep in the output hidden state and which parts to remove. Then, so we take the steady state CT, we pass this through 10H. So here we are not passing through a neural network or 10H layer. We are doing a point-wise 10H operation. We multiply with the OT vector to see which of the values should be kept from the steady state and which needs to be removed. Then we output the hidden state. So here is the hidden state that now it can be fitted into the next time step. And also we're copying this here and we can use it as an output, or we can just you can just ignore the output and just keep running this and use the output from the last time step. Please note that the 10x operation that we are doing here is different from the 10x there because we are not having any kind of matrix multiplication. This is not a 10x layer, it's a pointwise operation of each values. So you see, let's see the mathematical formula for OT. So OT is equals to sigmoid of WO dot product HT minus 1 HT. So this is a concatenation of HT1 and HT minus 1 and HT. And this is a weight matrix for this sigmoid layer. Plus this is a bias matrix for this sigmoid layer. And then we are passing through the sigmoid itself. And then we get the OT and we multiply with OT with 10H of CT. So here we are not having any kind of weight because we are not having, this is not a neural network layer, this is a pointwise operation. So for each of the values in CT, we'll pass through 10H and we will multiply with OT, and this will filter the set state to give us the output HT, which can be fit into the next time step or can be used as a output. Now that we have covered the each of the components of LSTM, let's look into the LSTM as a whole. So this is the whole picture of LSTM where we have all the components from the LSTM. So first thing is the XT, which is the input token, and this is the vector representation of this token. And we have the hidden state HT minus 1, which is of size 2. So this is also a vector of size
We have
2.
one more alternative
The
to LSTM,
dimension
which is
of the
called
vector of
GRE or
hidden
gated
state and the
recurrent
steady state
ED.
will be same
It's
because
simpler than
the
LSTM and it's also
steady
widely
state
used.
is producing the hidden state, right? We saw that in the output here, the hidden state is calculated from the steady state. So the dimension will be the same. So this is the hidden state from the previous time step, which is of size 2, and this is the input, which is of size 3. We do a concatenation of the both to get a vector of size 5. Okay, so this is the concatenated input, which will be input to all the layers in this LSTM unit. So the first component in this LSTM unit is the forget gate, right? So this is the forget gate where we have this sigmoid layer. In this sigmoid layer, we are having two neurons, and this is the input that we are having. So this is all the weight connection between the input layer and this sigmoid layer. So we'll have a weight matrix of size 5 cross 2, as we are having 5 inputs and two neurons in this sigmoid layer. And we need to have two neurons in the sigmoid layer because the output should be of dimension, output should be of size 2 only. Because we'll do a pointwise operation with the steady state. So the dimension of the FT vector that we get from the forget gate should be same as the steady state. So that's why we are having two neurons in this sigmoid layer. Now, next thing is the input gates. So this is the input gate. This is the sigmoid layer of this input gate. And here as well, we see the similar structure as the forget gate. We have this 5 inputs and then two neurons in this sigmoid layer. This will give us the vector IT. So next thing is the 10H layer or 10H layer. So in this 10H layer, we see there are two neurons similar to other layers we have seen, and we have these 5 inputs. So we'll have 5 cross 2 connections here as well, and we'll get a output of dimension 2. The output from here is the new possible candidate cell state. And we do a pointwise multiplication between the vector IT and the new candidate cell state to get a candidate cell state that can be added to the cell state that we have currently. So let's look into the updation of the cell state. So first we do pointwise multiplication of vector FT from the forget gate to update the cell state so that we remove the unnecessary information from the cell state. And then we do a pointwise addition of the candidate cell state from here so that we update the cell state with new information from the current input or from the current time step. That's how we get the new cell state CT. And this CT is used for getting the hidden state. So let's look into the output gate first. So this is the output gate. Here we see that we have a sigmoid layer with two neurons, and similarly we are providing the concatenated inputs in this sigmoid layer. So we have here again we have this 5 cross 2 connections, and we get a output of size 2. So to calculate the hidden state, first we pass the cell state CT to pointwise 10H operations. So here we are not doing any kind of matrix multiplication because this is not a 10S layer. Here we are doing pointwise 10S operation of on each of the values of the steady state vector. So for each of the values, we'll pass through 10H function to convert the value between -1 and +1. After converting the value, we do a pointwise multiplication with the output from the output gate, that is OT. So once we do pointwise multiplication, we get the hidden state HT. So this hidden state is fed into the next time step, or it can be also used as output from the this time step. This is how we calculate the hidden state and the steady state in LSTM. So one more thing that I want to discuss is this conversion of XT as token into vector form. So we use embedding layer to convert the token into some vector form. The vector form of this token is also called embedding. That's why the name embedding layer. So the embedding layer is responsible for getting the embedding for a token. And it's similar to the word-to-vec model, but the word-to-vec model will give you a static vector representation for a given word, but the embedding layer will give you a dynamic representation based on the context of the word around the in the sentence. Let's look into an example for better understanding. So let's consider the word bank and two sentences which uses bank. So first sentence is I went to the bank yesterday. The second sentence is we had a picnic by the river bank. Now the word bank is same in both the sentences, but both of them have different meanings because the context is very different. So if you use the word-to-vec model, you'll get the same vector representation in both the cases. But the embedding layer will give you a different representation based on the context. And so the vector representation is much better than the word-to-vec model. Thanks for watching. If you have any queries, please comment. I'll try to get back or create a separate video to answer your queries. See you next time. Bye.